Hello everyone and welcome back to our introduction to cybersecurity class. So in this video we are still discussing fundamentals of cryptography. We already introduced cryptography in the previous video and now we are going to discuss the different cryptographic algorithms. Cryptographic algorithms are special methods we use to secure information. So there are three main types. The first type is, let's say, hash algorithms. These take data and turn it into a fixed size string of numbers and letters, which helps check if the data has been changed. Second, we have symmetric cryptographic algorithms. In these, the same key is used to both encrypt and decrypt the message, meaning both like the sender and receiver need to have the same key. It's symmetric, okay? And finally, we have the asymmetric cryptographic algorithms. These use two different keys, one to encrypt and another one to decrypt. This way, the sender and receiver don't need to share the same key, okay? Each of these types helps protect information in different ways. So, to protect messages using cryptography, there are different ways. So, one way is called one-time pad or OTP. So, this is like a very secure method where the message is mixed with random key. The key is a long list of random letters, and the person who gets the message must have the exact same key to read it. Okay? Another way is stream cipher. So stream cipher changes one letter or number at a time, replacing it with something else, which is, let's say, quick way to encrypt messages. Another way is block cipher. And block cipher looks at the whole part of the message at once and changes it, making it more powerful than the stream cipher. Okay? And also there is the sponge function that takes any length of input and changes it like into a string of any length that you want, which makes it like very flexible. Okay, so these methods are used for different needs depending on how secure and fast the encryption should be. In this figure, you can see how hash algorithms are used to check if a download is safe. When you download the file, the website gives you a unique digest. It's a string of numbers and letters, okay? And this digest represents the file. So after downloading, your computer creates its own digest for the file. If both digests match, it means that the file is safe and hasn't been changed. If like they don't match, then the file may be corrupted or let's say tampered with. So this process keeps the file secure and ensures that download is trustworthy. As you can see here in this figure, it's shown by the 2.53 value, okay, in this figure. In this figure, we see how symmetric cryptography works. Here is the process. Bob, the sender, has a confidential memo, which is the plain text, that he wants to send securely. He uses an encryption algorithm along with a key to scramble the message into ciphertext, which makes it unreadable. This encrypted message is sent to Alice, the receiver. Alice uses the same key because it's symmetric. And remember, we said for symmetric cryptography, they both use the same key, okay? So Alice uses the same key and a decryption algorithm to turn the ciphertext back into plain text. so she can read the original message that was already sent by Bob. Okay, so the key is shared here between Bob and Alice, and it must be kept secret to ensure the message stays secure. This is how symmetric cryptography ensures that, like, only the intended, let's say, recipient can read the message. Now, when it comes to asymmetric cryptography, there are two keys that are used. It's not like the symmetric cryptography where we use only one key. In asymmetric cryptography, two keys are used. One is called a public key, and there is also another one which is a private key. The public key is shared openly and can be used by anyone to encrypt a message, while the private key is kept secret and it is used by the recipient to decrypt the message. Okay, both keys now work in both directions, meaning the public key like encrypts and the private key decrypts. So in this figure, we see like how this works with a confidential memo. But now the sender wants to send a secure message to Alice, okay? He uses Alice's public key because every user has their own public key and everyone else has access to that public key. So Bob, since he wants to send to Alice, he can see the public key of Alice, and now he's going to use the public key of Alice, okay, and like an encryption algorithm to scramble the message into ciphertext, okay? Now, Bob is like sends the ciphertext to Alice, and Alice then uses her private key and a decryption algorithm in order to turn the ciphertext back into plain text, which can read, okay? She can read, okay? So this method ensures that only Alice, who has a private key, can decrypt and read the message, keeping it secure from others. Here in this figure, we have points labeled A, B, C, and there is a minus C there. You see the minus sign? Okay. And these points now are on an elliptic curve. Okay. So the purpose of these points is to like show how elliptic curve cryptography, which is the ECC, works geometrically. So what we have here for each point, um, like each point has its own coordinates. Like for point A, we have the coordinates, so minus 2, minus 2. So point A is at minus 2, minus 2. Minus 2 if we see it along the axis, like axis, and there is the y-axis, then there is another minus 2. Okay, so point B is at 1, 1. Point C now is at 2 and minus 2, and here the minus C is that minus like sign, it's like because it has a relationship with the point C, okay? So I call it minus C. So this like minus C is the reflection of C across the X axis, okay? So uh, now so the ECC, the elliptic curve cryptography, here, like what we have, the points on the curve are used to create a pair key, okay, for encryption and decryption. So the process involves using the curve's properties to perform mathematical operations like adding points together, for example. Okay, by adding, let's say, or let's take the example of points like C and B on the curve, okay? So what we can do, you can generate another point, okay, which helps in creating the public and private keys used for encryption. And so this geometrical approach makes the ECC like both secure and efficient, which is why it's widely used in modern cryptographic systems. In asymmetric cryptography, the digital signature algorithm, DSA, creates a digital signature that does three important things. It verifies who sent the message, prevents the sender from denying they sent it and ensures the message hasn't been changed. When it comes to key exchange, there are different methods to securely like share keys. For example, Diffie-Hellman, like DH, helps two parties exchange keys safely, while Diffie-Hellman ephemeral, like DHE, makes the keys temporarily, let's say, like it makes like the keys temporary, like for extra security. And elliptic curve Diffie like Hellman, ECDH uses more efficient math in order to do the same thing with, let's say, smaller keys. So lastly, there is the perfect forward security, the PFS. This ensures that even if a key is later stolen, past messages stay safe. These methods keep our communication secure and private. Thank you for watching, and in the next video, we will cover encryption through software.